session of Creative Weekend Talk, episode 166. We are delighted to welcome you all to the special event. We are thrilled to announce that Creative is now officially registered under a trust, marking an important milestone in our mission to share and grow knowledge. Guided by our tagline, Knowledge Square, sharing knowledge increases our knowledge. We continue to explore diverse and provoking topics every weekend. Today's topic is Physics in Play at Satellite Control, Master Control Facility, Hassan, ISRO. This session will offer a fascinating look into the role of physics in satellite control and the work done at ISRO's Master Control Facility. Our guest speaker for today is Sri Ananda HD, whose expertise will give us valuable insights into this specialized field. As always, our weekend talk is held on Zoom from 3 to 4 p.m. and live streamed on our YouTube channel Creative GBD. Without further delay, let's begin this session. I welcome Govardhan, volunteer of Creative team, for the guest introduction.
Good afternoon to everyone. My name is Govardhan, volunteer of Creative. It is my privilege to introduce our distinguished speakers, H.I. Ananda, a renowned physicist, space scientist, and educator with an illustrious career spanning 4 decades. Ananda is a Bachelor of Science degree in Physics, Chemistry, and Mathematics from Mysore University, a Master of Science in Physics with a specialization in solid state physics from Mangalore University, and a postgraduate diploma in computer programming from Mysore University. Sri Ananda began his career in physics at Malad College of Engineering, Vizag, and briefly pursued research at the Indian Institute of Science, Bangalore. He later joined ISRO's Master Control Facility in 1986, where he played a pivotal role in satellite operations, spacecraft data analysis, software development, the space assessment, head of ISRO. Sri Ananda held positions including head of the computer system and simultaneous group director of ISRO systems, member of the ISRO Software Control Board. His expertise contributed to the development and implementation of mission critical software adherence to IEEE software standards and successful executions over 50 satellite pre-launch and launch and orbit raising activities. Beyond his professional achievements, Sri Ananda has made significant contributions to education and being a guest faculty member, mentor to engineering students, and a dedicated advocate for science popularization to inspire young minds. A life member of esteemed organizations such as the Computer Society, the Astronautical Society of India, and the College of Physics and Chemistry. He has published technical papers and contributed to knowledge and improvement programs across
Hello, sorry to disturb this session. I think Govardhan doesn't have network connection. Over to Anand sir. Sir.
Yeah, I'm able to hear.
Okay, sir. I think I apologize you for the network issue of Govardhan. Can you uh, continue this session?
Yeah, I can start. Yeah, before let me
Thank
share.
you so much, sir. I welcome you.
I'll share the screen.
Over to you, sir.
You're able to see the screen?
Not yet, sir. Not yet.
Hello, I've shared it actually.
No, sir. Check it once again. Now it's visible, sir.
Okay, now you are able to see?
Yes, sir.
Okay. So you want me to speak in Kannada or English?
So I think English is preferable because so many people are there understand Kannada. That's why.
Fine, let me thank uh, organizers of the creative for giving me an opportunity to share my knowledge with students. Actually, a lot of information is available. Let me see how much I will be able to speed up and complete. So, yeah. Now, whatever the first slide you are seeing is we have two campuses, master control facility at Hassan and master control facility at Bhopal. So this is the front campus of Hassan, whatever you are saying with the green lush beauty. Okay. Now the first question comes is what is the need of establishing MCF, Master Control Facility? See what has happened in the late 70s. There was a committee constituted to look at whether the satellite communication is useful to the country. So for that reason, there was an experiment called the satellite instruction television experiment was done in around 1975 or so, going all across the country, where they established the receiving and reception facility. And in Karnataka, in Gulbarga was the place. So they collected the data for sizing of the satellite, whether suppose if the communication satellite is established, whether useful to the country. Based on that, the sizing of the satellite was done. So finally it was decided to go for 4 communication satellites procured from US. So in the INSAT study, actually which is jointly conducted by ISRO and MIT in 1970, they identified that a dedicated control center has to be established for control of the INSAT satellite. Now, it was also noted that the satellite control center which is going to be established should be near to the place where satellite is going to be built. And also that since India is a country where we are spending public money, we should be aware of the utilization of the funds properly. So with that taking into consideration, the initial 4 satellites, many of the payloads, multiple payloads, like normally in the present, if you take this 24, now we have dedicated satellite for communication, weather forecasting, and etc. But those days, taking into economy into the consideration, the utility of the project, multiple payloads were put on the same satellites. That's why the INSAT 1 series and even initial INSAT 2 series are multi-purpose satellite, where you had both communication payloads, the weather forecasting payloads, and the disaster warning, and all societal applications which useful to the country. Okay. So it is also essential. The committee, when they filed the application for filing in 1976 for ITU for the corresponding frequencies to be used, it was very clear that C and S band frequencies are going to be used for the TTC operations. Now, whenever we want to establish a control center, yeah, there were some constraints. That is, initially, suppose if you want to establish any RF station, the RF station should be minimum 500 kilometers away from the neighboring country. So suppose if you look at the geographical map, 2 places were identified initially. One is at Anantapur, another one at Hassan. Now the nearest station which was there in the south, if you look, was on those days was the Jaffna. And then if you go up, now you have, if you go in the west of the country, you have Pakistan, and right side you have Bangladesh, and still you go to China. So with all this consideration, the control center should be minimum 500 kilometers away from the nearest RF microwave station, so that it doesn't fight the operation. So now, it was very clear that the control center has to be minimum 500 kilometers away. And I also told that when the committee recommended, the control center should be very close to the place where satellite is going to be built. So 2 places were identified, and finally looking at the better connectivity and other reasons, Hassan was selected as the place. Now, before we go to the communication satellites, it is essential to know in order to find, coming to the geostationary orbit, there was a German mathematician called Kepler who proposed three fundamental laws. So what he said is the time taken by the planet, all the planet to go around the sun, is called it as evolution. He also stated that all the planets are moving in elliptical orbits around the sun with sun in one of its foci. The second one is called the law of areas, where all the heavenly bodies, they seeps out in equal areas in equal intervals of time. Our point of interest is the third law of Kepler's law of planetary motion, where suppose if T is the period of revolution of the satellite, T squared is proportional to A cube. And if you consider if it is a circular orbit, T squared will be proportional to R cube. So now this is the one. Now suppose for a geostationary orbit, for a stationary observer standing on the surface of Earth, the satellite should appear to be stationary and not moving. Now Earth actually takes 24 hours to go around its orbits once. So if the satellite has to be stationary with respect to an observer, the satellite also should take 24 hours to go around the Earth once. So now, based on this Kepler's third law, T squared is proportional to A cube. If you place a satellite approximately at the distance of 36, suppose if you put all the numbers and the Earth radius, if suppose Earth radius is 6378 plus or minus 11 kilometers, because of the semi-major axis and the semi-minor axis, the total the distance comes to around 42,165.8 kilometers. At 42,165 kilometers, including the Earth radius, if you remove that, it is 36,000. So if you keep the satellite at a distance of 36,000 kilometers from the Earth's surface, for a stationary observer standing on the surface of the Earth, the satellite will not appear to move. Now, suppose if you keep the satellite few 100 kilometers away, one will overtake. If you keep 100 kilometers above the 36,000, the other fellow will lag. So now, this is not a sacred number. It's basically based on your Kepler's third law of planetary motion. So if you keep a satellite at a distance of 36,000 kilometers above the Earth's surface, the satellite also takes 24 hours to go around the Earth once. Such an orbit is called a geostationary orbit. In other words, in Kannada, it is called Bhustira Kaksha. And the corresponding satellite which is placed in the geostationary orbit is called a geostationary satellite. So basically, it says that the satellite is visible continuously to an observer standing on the surface of Earth. So typically, this is the pictorial representation where you are able to see the law, the first law, where all Ella Akashakaiಗಳು are going around the sun once, and second one is the law of areas, and third one is the Kepler's law of planetary motion, which I explained. Now, so as I already told you, so if the satellite revolves on the Earth around the equatorial plane from west to east, the period is equal to 20 years. So such an orbit is called a parking orbit or a geostationary orbit. So typically, this is the this is actually the equatorial plane. To visualize this equatorial plane, you can visualize Earth as an apple. You cut the apple, you take the half of the apple, whatever plane you are getting, the equatorial plane. Assume that I am drawing an imaginary line from the satellite to the equatorial plane. The point at which the imaginary line drawn from the satellite to the equatorial, when it cuts the equatorial plane, that point is called the subsatellite point, what is mentioned here. Now, so subsatellite point is very, very important, because the subsatellite point has to be controlled in a very controlled way. Now, suppose if you take in a 24 hours orbit, the locus of the subsatellite point, if you trace it, it looks like a figure of 8. Yeah. So now, then probably there are other reasons why Hassan is selected. One is Hassan is there on a strong Deccan plateau where it is capable of bearing the load of the Earth stations, and there is no much floods and earthquakes. And moreover, suppose if you have a control center and a tracking station at Hassan, if you point out upward, you will be able to track the maximum number of satellites visible, meant from 0 to 150 degrees. Almost all the satellites which are there in that 0 to 150 degrees, you have a large maximum visibility arc, and you have got less interference from other telecommunications installation, which I already told you, like it has to be there 500 kilometers away, and land availability, and it's very close to the headquarters. which was then Bangalore, because the satellite was design center was there at Bangalore. With all these reasons, Hassan was selected. Now, what we do in Hassan? See, basically, whenever a new launch takes place, we hire a set of network stations to get the data continuously, because the satellite is not visible over Hassan all the time. So we hire a group of stations for a continuous visibility and tracking and to support the mission. So we coordinate with all network stations for the pre-launch readiness. We also monitor all the INSAT, GSAT, and the IRNSC. Now, currently, the name, whatever the nomenclature has been changed now. All the communication satellites are called communication satellite CMS, and the meteorological satellites are called EOS, Earth Observation Satellites, and the IRNSS, which is called the actually Indian GPS system, Indian Regional Navigation Satellite System. Now it is called NVS. Okay, so depending on that, that is a new nomenclature which has been given. So MCF controls, monitors all these class of satellites, and finally, when the satellite is put into the right position, whatever the payloads which are being carried out, they are tested on the ground, and the results would have been noted down. But when the satellite is positioned, there is a harsh vacuum. It is essential to establish the performance of the payloads before it is made operational. So to assess that, we conduct a series of tests, what is called the in-orbit test, to find out the operation performance of all the transponders. And then suppose if there is any limitation, we note down. With that limitation, we say that we have to operate the satellite, then the satellite will be dedicated to the nation. And we also maintain, it is something like once the satellite is ejected from the rocket, it is something like the baby is born. So once the baby is born, bringing up and maintaining till the death of the satellite, it is job of MCF. These are the works which we do. So this is a site data of Hassan. What is the national, how far it is there, what is the rainfall, and all these things. And total campus in Hassan, you have got in the around 100 acres. So this is what I was telling, means that from 0 to 155 degrees, all the satellites which can be tracked, you have a very large geo-arc visibility from Hassan. So this is just to note down, as if suppose somebody is not visited Hassan, we have a main campus, we have a satellite control center, we have a test station, we have got power backup facilities to support the operations. And similarly, they have got certain other facilities. It is only an academic interest. We can skip this actually. Yeah, typically, till now, there are 31 satellites have been controlled from Hassan and Bhopal. Basically, we have two control centers which are there in the same longitude, 82.5 degrees. So basically, Bhopal Control Center is established to address the disaster management in the case of if something happens to Hassan, or if there is a terrorist attack or a natural calamity, the space exits is going to get disturbed. So in order to protect the space exit, because we are maintaining more than 35,000 crores worth of space exit, so it is very difficult to re-establish or get back the space facility. So so to avoid any natural calamities, we have another control center. Some of the satellites are controlled from Bhopal, and majority of the satellites are controlled from Hassan. In case of any problem in Hassan, satellite operations are handed over to Bhopal and vice versa. So totally there are 22 communication satellites, there are 9 navigation satellites, and totally 31 satellites have been controlled from Hassan and Bhopal. And typically you are seeing the split wise. Actually, for each country, even though we have 31 satellites, we don't have the luxury of having 31 slots. For each country, there is a organization called International Telecommunication Union, which allocates the slots depending on the request. Even though we have 31 satellites, we don't have 31 slots. So based on your request, so each country is allocated certain number of slots to maintain the satellite. Since we have certain 31 satellites, it is essential. For example, you have got a site, you have a 60-40 site. If you want to go for a bigger building, you may go for apartments. Similarly, if you want to control more number of satellites, we have to position more than one satellite at the same longitude. So maintaining and controlling more than one satellite at the same longitudinal slot is called co-location. So co-location is actually basically maintaining and controlling more than one communication satellite or any other navigation satellite at the same longitude. Only thing is, The operational difficulty will come because there are, when you want to maintain the satellite, when I to attain operations, the operations has to be done in a sequence. So you cannot do it is a little bit tough. It's not that easy. So you can see, particularly in 55.5 degree, there are 6 satellites which are being controlled. Yeah, I have just given the similar how many satellites, which are the longitudes, which are the spacecraft which are being controlled at each longitude. This graph, this particular picture shows that. So this is a typical picture. This is a very old picture. This is a typical representative of a control center where you have the computer, the RF systems, and the other areas which are used for operations. Similarly, one typical 14-meter antenna which is used for tracking the satellite, and the corresponding RF equipments and the high power amplifiers of a typical Earth station is being shown here. And similarly, to have we need a continuous power backup. The corresponding, suppose in case of loss of power, we have to use the diesel generators, and each critical areas are supported by battery banks. So because it is the generators has to be operated, to be switched on manually. So there is a time period, the battery support. So all the critical Earth stations are supported with diesel generators. Yeah. Now let us come to the types of orbit. Already I told you the satellite, that is one is the geostationary orbit, which we call it as a parking orbit or Bhustira Kakshe, where the satellite orbit period is same as that of the Earth. We have got sun synchronous orbit, where the polar satellite, the remote sensing satellites, where they go around the pole to pole around 900 to 1,000 kilometers orbit. And we have got near Earth or polar orbits or microgravity experiment, or even low constellations, like what example Elon Musk is having a set of that low satellite for high broadband connectivity. So they are all near the satellites. So typically, so MCF establishment has grown in terms of facility. So actually in 1982, when the program started, we had only 2 14-meter antennas. So over a period of time, you have got 31 spacecrafts out there. So normal operations of this, once a spacecraft is put into its orbit, we need one minimum 7.2 meter terminal to track and collect the data. So this particular time, this next graph shows how so this is actually in February 2006, how the MCF campus was there, how was it populated. You can see you don't find too much crowded. We have got 4 campuses in the mainland and in the opposite land. Similarly, as on today, you can see in February 2020, if you look at the Google map, so many Earth stations have come up. So this is so what I'm telling is trying to say, with respect to, even though satellite earlier there are more than one launcher, maybe 3 to 4 launches is to take place, and each 3 to 4 launch we need actually one terminal, but realizing a terminal doesn't have it. It is not may not happen in the right time. So some compromises one has to make. So this is the evolution of establishment. So this particular graph shows how the satellites have grown over a period from 1982 to 2022. And similarly, how many antennas in 1982, we had only 2 antennas. Today, we have around more than 80 plus antennas up to 2022. Now it is still more. Okay. So typically, this is what I was telling. So all the geostationary satellite or the communication satellite around the equator. So that is what the first picture shows. The second is a polar orbit, where the remote sensing satellite go around the pole to pole around 900 to 1,000 kilometers orbit. Now, basically, what we call, when I say inclined, see, normally the angle subtended between the satellite orbit and equatorial plane is called the inclination. So normally the inclination has to be very, very small as far as the geostationary orbit is concerned. It should be less than 0.1 degrees. For inclined orbit, where particularly in the navigation satellite, there are satellites which are inclined up to 29 degrees for the case of array, and the maximum availability of number of satellites at any instant of time, typically around 4. Yeah. Now, with this basic kind of inputs, our life cycle, the geostation. So once a satellite is put into an orbit, it consists of 3 distinct phases. One is the launch phase, or the initial phase operations. Next, once the launch is over, we have got the satellite. It is like baby is born and baby starts growing. So that is on-orbit phase of operation. The third one is the end of life mission. When I say end of life mission, whatever fuel which is carried out in the satellite is going to end. So it is going, so we have to deorbit the satellite. So there are three typical distinct phases. So now in the phase of when the launch early phase operations are important and critical for any satellite mission. There are different kind of launches. We have the space shuttle, and you have got the Delta and you have got the Russian Proton, where we directly space the satellite into a direct geostationary orbit, where see, normally when we in a particular orbit, the point which is very near to the Earth, we call it as a perigee. The point which is very closer to, which is farther away from the Earth, is called the apogee. So normally the satellite is get injected by the spacecraft. The spacecraft get injected by the rocket into an orbit of 350 by 35,000. Means that apogee will be almost geostationary, whereas perigee is very near to the Earth. You will see that next diagrams. So now what happens is, once the satellite when the rocket lifts off takes place, the telemetry transmitter which is there, which sends the data, will be switched off. So prior to when the countdown starts, a few hours before that, there are so many activities which are carried out, launch related activities, or initialization sequence may happen few 10 to 15 hours before that. So once the liftoff takes place, the telemetry transmitter will be still on. 100 seconds after liftoff, we are interested to know there are certain activities which takes place after liftoff, whether it is a snap sequence or the closing of the venting of the valves. We want to ascertain the first cut assessment of, we are interested in assessing, we want to know the health of the satellite still being inside the rocket, not being ejected. So there is a one radar, what is called MOTR, multi-object tracking radar, which is there in Sriharikota, which tracks the locus of the rocket, and whatever the data which is collected, it is transmitted, it is sent to Hassan via dedicated links as a UDP form, and the data is acquired from our computers. Or then those data which is there, which is validated, which is actually the tracking angles. So that those angles are fed to one of the tracking antennas at MCF. The antennas are driven so that we track the trajectory of the launch vehicle. And at some point of time, we were able to get the signal from the spacecraft still being inside the rocket. So this is what is called CDM. So once the satellite data gets locked, we'll get the data almost for almost 3 minutes. So satellite still being inside the rocket, 100 seconds after liftoff, we will have the first cut assessment whether satellite health is okay or not. So this is very, very important activity. So this can be done only for Sriharikota launches, not for French Guiana or any other country launch. Okay. So this is a typical picture where how the antenna is tracked. We call it as the azimuth and elevation angles, typically around 300 seconds of data. Okay, this is actual data of the tracking of one of the launches, but I have not put which spacecraft is that. It's typically, so the CDM helps the subsystem engineers and MCF to assess the performance of the spacecraft, still the satellite being not ejected from the rocket. So now what we do on the launch day, we configure everything in redundant mode. We will have 2 Earth stations configured with both with uplink and downlink facilities in redundant chain, and we have the connectivity with the network stations for visibility to take care of visibility and non-visibility period. All the communication links at the launch pad and network stations we pre-verify, and the mission computers with redundant power state supplies also will be checked and kept verified. So these are all, we call it as before the liftoff. There is for example, before liftoff, there is a no-go condition, means that everything in MCF is okay. So all these chains with redundancy, we have to give go. So once we say go, then only liftoff takes place. If there is a problem in any of these checks, probably the launch hold takes place, it may go to the next day. So now typically these are some of the international stations. We hire a station in Fillmore in USA, the other one in Fucino, and we have our own station in Indonesia called Bayak. So these 3 stations in together, because when the satellite is not, when the liftoff takes place, as already said, in order the satellite to be geostationary, the satellite should take 24 hours. But once the satellite get ejected from the rocket, it will be ejected in orbit of 300 plus by 36,000 kilometers. Means that it will be an 8 hours orbit. So the satellite is will be visible only over Hassan only for 8 hours. When the satellite is not visible, the other stations like Intelsat stations, they track the satellite and send the data over dedicated links. They also do whatever what our equipments are there in these international stations. So the commands are sent using their facilities, their antenna to dedicated link through our equipments positioned in these stations. And also, in order to precisely establish whether the launch is okay, where the satellite is there, what it is positioned, and in order to find out its orbit, we have to carry out what is called, we have to find out the slant range. It means that we do an operation called ranging. We send a signal and receive the signal with a delay. This is basically a Doppler effect. So ranging operation is also done from all these stations. So they send the data for orbit determination purpose. So typically this is also gives the where it is the main control center is there in Fillmore, which is in US. Yeah. So this particular diagram I'll explain. Later I'll just briefly rush through what we do. See, this is what I was trying to say, that initially the satellite is injected to a elliptically parking orbit of, this is what the nearest point to the Earth is called perigee. The farthest point is called the apogee. This distance is almost 36,000 kilometers, whereas this is only 300. Now, 80% of the fuel which is carried out in the satellite is used to raise the perigee height from 300 to 36,000 kilometers. So that is done by using a very series of set of complex maneuvers, what is called as the liquid apogee motor firing, where we use a heavy engine to, we initiate there, almost for 90 minutes, the engines will work, and almost 3 such burns are done. So after first burn, you will have an intermediate where the perigee height is raised, where the orbit will become around 16 hours. And similarly, so typically these 3 burns will take around 1 week. So after 3 burns, you will have the perigee height raised from 300 kilometers to 36,000. So typically the satellite time period become exactly, it may not be 24 hours, near the geostationary orbit it comes. Now what happens is, most of the appendages which is carried out in the satellite, it will be in the stored condition. So we have to get it open. So the deployment of all the appendages is one of the major crucial activity. For that, many complex maneuvers have to be done, where the satellite has to be reoriented, the orientation where you orient it in such a way that the sunlight should fall on. For example, you can see the solar panels getting deployed here. So where it is oriented towards sun, and finally there is a deployment of, and there is a orientation again. So there is another solar panels getting deployed. Finally, the antennas are so finally you will have a very, very deployed spacecraft almost in the geostationary height. Okay. So this is a typical activity what we do in almost first 1 week. In detail, I am just like, so this particular sequence, this almost that is rising of the orbit, satellite orbit by that is perigee height from 300 to 36,000 by using heavy engines called liquid apogee motors by 3 complex maneuvers. It has to be pre-planned and to be done in a planned way with the participation of all subsystem engineers and everything. It has to be well documented and reviewed. Okay, I have just told in a nutshell. This is a critical activity which is being done. So satellite is finally positioned at reaches the geostationary activity. Yeah, typically when the satellite is get injected, typically the semi-major axis, that is what we call the apogee, is at 42,165, and the inclination, that is the angle subtended between the orbit, so satellite orbit, and the equatorial line should be 0, and the eccentricity also should be 0. So typically, now I have explained that. Now, for example, the moment a liftoff has taken place, now the satellite is coming over Hassan. So normally after liftoff, 90 minutes after liftoff, the satellite is visible. For example, if it is a French Guiana launch, the satellite is visible over after 90 minutes after launch. So now you have to acquire the signal. So in order to acquire the first signal, what we do, we point the antennas to a position what is called the AOS position, called acquisition signal position. Typically, the two antennas driven. In one of the antennas, we program the, we will load a file which will automatically track. The other one, we will track the in a manual mode based on our expertise. So we configure two antennas, one in program track mode, other one which is called the manual mode. Manually, you track the rocket, the satellite to acquire the first signal. So once we're able to track the signal, we get the confirmation of a signal through what we call AGC level, called automatic gain signal. Finally, the signal gets locked on a spectral coil. So once the signal gets locked, we call it as AOS. So once the signal is locked, we do the first initial checks by the subsystem engineers. There are other confirmation checks which is done with respect to where once the satellite gets ejected, there are certain activities done before it is ejection, and one test command is sent to verify that we are able to communicate with the spacecraft. Now, in the next few hours, we don't do many major operations. We try to receive, say, tele means distance, metry means measurement. So distance measurements, so you're trying to get the information from a distance, that is called telemetry. So telemetry, we try to get the data from all the network stations whenever, for help monitoring the health of the spacecraft, whenever the satellite is not visible over Hassan. Second thing, already I told you, we want, for example, in order to locate the position of an object in space, precisely we should know two things. One is the current position and its rate of change of position. So basically R and R dot we should know. So in order to know that, we do already, I told you that we do a what is called the ranging operation, which is done from the all network stations. And this network ranging data received from all network stations is fed to our through computers to our flight dynamics. They do the orbit determination and find out whether the maneuvers which is being carried out is the right place, whether it is what is the drift rate, which longitude, all these things. And similarly, we have to maintain the spacecraft orientation that the solar array is always pointing toward the sun so that solar power generation is there. And similarly, what happens is because we have not positioned the satellite in the right orbit, because we have to raise the perigee height by 300 to 36,000. So it's a drifting satellite with a fairly high drift rate. Now, in the process of drifting, the drifting satellite passed through already existing operation satellites of other countries. So it may so happen that whenever you want to do a command, so we have to inform all the satellite operators that our satellite is drifting. In case there is in case, because the commanding frequency which is used by our satellite may be same as the similar commanding frequency used by the other operator. So we have to a priori inform the other satellite operators about the arrival and departure of their specific satellite which are being controlled. If there is a problem, we have to take measures that the operating satellites of other countries are not affected. That is what you call it as flyby coordination. Similarly, say like a human body, the satellite subsystems also undergoes extreme temperatures. So when the temperatures reaches low, we have to switch on the heaters. When the temperatures goes up, we have to switch off the heaters. Heater management is another important thing. And since it is not reduced in orbit, certain times there will not be generation of power because Earth shadow will fall on the panels. So that time satellite undergoes an eclipse. Yeah. Second thing is, in order to position the body rates, there are gyroscopes are available, which gives the body rates and the angles. So basically, these gyros are very, very sensitive to temperature. And so if there is a drift, its performance is not guaranteed. That's why the gyros has to be calibrated regularly. And gyros has to be calibrated using certain optical sensors as a reference, using a sensor or some of the sensors which are available in spacecraft. And so in order to do a gyro calibration, you have to take a suitable part in the orbit where you have the Earth should be visible very clearly, and there should not be any other heavenly object like sun and moon coming in the field of view of some of the sensors. So we have to ensure that whenever you want to do the gyro calibration, there are certain constraints one has to follow. And lamp firing, I already told you is done to the geostationary height by adding delta velocity at the perigee. So we already now multiple bulbs are done. And similarly now, particularly which orbit, whether the first orbit or third orbit, sixth orbit, seventh orbit, is based on particular planning is done based on the visibility, and also taking into consideration sun and moon intrusion. They don't come in the field of view of the Earth sensor. So there are other constraints. So there is very accurate planning is required for planning the plans. Say typically approximate 80% of the fuel loaded is consumed for the last. So remaining 20% of the fuel which is left out in the satellite is used for controlling the satellite throughout its life period. So already I told you the stored appendages, LoRa panel, sails, and reflectors, they're all deployed. Finally, what happens is, see, basically what happens is, see, we are here. Sunlight falls on us also, but we don't feel the pressure from the sunlight. But when you place a satellite at a 36,000 kilometers, the solar radiation, the photons impinge on the solar panels. So over a period of time, it introduces unwanted. Basically, what happens is, when we want, for example, we have eyes to look at observe an object or observe a person or interact with a person. Similarly, there is a sensor on the spacecraft which is called an Earth sensor, which is always looking toward the Earth. So as long as the Earth sensor is looking toward the Earth, we say it is called Earth locked. So Earth locking of the Earth sensor is a prerequisite to make or to have the satellite data coming or tracking the satellite in its position. So now what happens is, I have already told you, because of solar radiation pressure and other things, it will generate an unwanted torque on the solar panel so that the satellite may get tilted. So in order to damp out unwanted solar radiation pressure, you have a bias momentum system which is looking at the pitch axis. So there are certain gyros which rotate with a specific speed. We call it as 3-axis stabilization. We switch on those, so we call it as momentum and reaction wheels. So now basically these reaction wheels or the momentum wheels are commanded to a certain speed because their speeds actually match with the resonant frequency of some of these active components like scan mirror, other things, and finally it generates the noise. So we have to ensure that the commanded wheel speed should be outside the natural frequency of some of these scanning mirrors. And similarly, we have got the magnetic torque because the Earth magnetic field also affects certain activity. So the magnetic torque which will compensate that is also switched on. So finally, the lamp firing is carried out. So after the final lamp firing, the satellite is there in that 36,000 kilometers, but we have to position the satellite at the right position. So for example, the satellite has to assume that the satellite has to the final longitude is 74 degrees. So after all the lamp maneuvers, the satellite may be there at 50 degrees. Okay, all the maneuvers have been carried out. Maybe satellite starts drifting at say 5 degrees per day. So in order to reach the intended position, it may take 4 days. So we allow the satellite to drift. Now, once the satellite comes to the intended position, say 74 degrees, which is the final position where we have to position the satellite, then we have to arrest the drift, or you have to stop the satellite to arrest the drift. So what we do, once the drifting satellite comes to its positional longitude, we do a very, very small set of maneuvers where we want to stop the drifting satellite and bring its drift net to near zero. And this is called a trimming maneuvers, which is also called as station acquisition maneuver, a set of maneuvers where sometimes when we try to stop the drift, it may slightly overshoot or undershoot. So it has to be done in a very, very planned way. Depending on the number of requirement, 3 to 5 trim maneuvers are done to position the satellite at the right longitude and the right eccentricity to start with the right argument of energy and with right collocation parameters. So now, after all, we have already launched the satellite, we have raised the orbit of the satellite, we have done the drifting of the satellite is already done. We have arrested, we have positioned. Already I told you in the beginning that we do what is called to assess the performance of the satellite. We do the in-orbit test. And once in-orbit tests are done, we dedicate the satellite for the operations. So the Prime Minister will dedicate, or whoever is there in the designate. So the active life cycle of the satellites starts here. Now, a new satellite is launched. We have raised the orbit. We have positioned the satellite. We have tested all the payloads, and we have dedicated the satellite to the nation. Now, so it is something like the satellite is mature. Now satellite here actually, it is something like baby is born and baby starts growing and baby becomes old. So in the same way, the satellite is positioned its right position. Typically, the lifetime for all most of our INSAT satellites have the life period of 20 to 15 billion years. So finally, the lifespan of the satellite is generally decided by the amount of propellant available left out after the initial fair operations. So there are cases where the missions also gets ended a priori. So during the normal fair operations, when the satellite is positioned in its orbit, we have to maintain its health, we have to maintain its attitude, we have to maintain its orbit, we have to maintain its collocation parameters, we have to manage its, because satellite undergoes an eclipse, so we have to do the payload management, we have to do the contingency handling, we have to assess the performance of different systems, maybe a daily subsystems or over a period of time. And we have the very, very crucial is the remaining propellant estimation, so that when we have to deorbit, and somewhere over a period of time, the solar panels, they degraded in performance, how much degraded. And similarly, there are other space activities like the Corolla mass injections, which may affect the performance of satellites. So we have to keep a watch on all these activities. So typically, so in each satellite, from the spacecraft, we get around more than 200 parameters, 2000 parameters, which we call it as telemetry. So whatever data we get from the satellite, maybe in the form of a voltage or a current or a status. So all of these parameters are displayed in a form where the people can understand in the form of display pages. So typically we have a suite of software, what is called a spacecraft health monitoring and control software, which is developed in ISRO, which has got both real-time capabilities and the analytical capabilities. So the schemas provide different kind of, and similarly, so when we operate the satellite, we should also look at whether any of the subsystems they are classing the limits. So the view, say for example, there are as you said, there are many components, there are so many areas, and each, as I said, the satellite undergoes different harsh conditions, like the temperatures may glow, temperatures may cross the limit. So suppose if there is only an information to be passed, so we call it as limit alarm. This is a soft alarm which generates visual alarm to indicate the spacecraft operators that such a particular subsystem or a parameter is crossing a limit and any action to be taken. And that activity is recorded in the history page. There is another kind of alarms, what is called critical alarms, where it generates both audio and visual alarms. One has to acknowledge, and there is an activity or a procedure one has to carry out to address, because that depending on what kind of the criticality of the alarm, one has to take an action to take the spacecraft with a safe condition. So there is another thing, as I said, typically we since it is a geostationary satellite, we receive the data every second. But there may be instances, because normally there are around in each frame we get around 128 words. So typically each parameter comes in 1 second. But for example, for certain reason, whenever we do special operations, we may be interested in looking at certain parameters continuously in all the frames. So there is a feature in the spacecraft, what is called the dual telemetry, where we can receive the same particular parameter in all the frames, so that that feature is available, so that one has to closely monitor that particular monitor that particular parameter to look at the spacecraft. Any anomaly happens during special activities. Similarly, what happens is there are certain payloads like the VHRR or the imager or the sounder, where we send a ground command to the spacecraft, where it will start scanning the Earth to take the Earth's picture in real time. But at normally it takes 30 minutes to take one Earth's picture. Once the picture is over, it has to go back to its position. But while going it back, because of some reason, it may not go to its position. There will be a mirror shift. So in such cases, in order to detect that there is a positional change in some of them, we do a near real-time monitoring, where we plot the data as a function of time as a graph. We call it a real-time graphic. And some of them as a PC mesh monitoring to find out is there any minor shift or spurious shift because of any anomaly, okay, or any change of the attenuation. All these things, there are other special monitorings we have. Now, I'm talking now. We are using English language to communicate because it's understood by many people. Similarly, we have to talk to the spacecraft and carry out certain activity. So satellite commanding is the way, is a regular activity with regard to subsystem operation and make a change in a satellite configuration. So now there are certain activities which has to be done every day. So what is done is we generate a computer-based schedule and which the timelines are given. So at the time of line, there is a scheduler software which is running in the background, which posts the commands to the space, which posts to the command in the command window. The satellite controller who is there in the console, depending on the criticality of the command, he will transmit the command to the spacecraft. So all planned and time-tagged activities are carried out through a scheduler. There are certain commands which we load the commands on the spacecraft directly, which is called condition based. There are certain activities which has to be done only one time in a day. So we call it as an operation directive, where we give the condition, okay, but we carry out this activity to an ops directive. Now what happens is, other than these activities, there are certain perturbations, there are anomalies which can happen on the spacecraft. Now, when a spacecraft anomaly happens, we may lose the spacecraft, we may lose the tracking of the satellite, we may lose the control of the satellite. So we may have to recover the satellite fast so that the users are not affected. So in order, for example, there are certain events where the spacecraft persons who are there in the console, they are not able to attend however, human response cannot match. So for such anomalies where we know there is an anomaly where action has to be taken fast and we have to take the spacecraft to safe conditions, there are automated events which we call it as there is a software which is running in the background which are called events, which looks for those anomaly to happen and sends the spacecraft. So it sends commands to the spacecraft, and the spacecraft are taken to the safe condition. Okay, so events are basically defined to handle known and repeatable anomalies whose signatures are known, where human tendency cannot repeat that in a very faster way. In the latest satellites, we have certain automated features, what we call programmable automated, where the switching on of the heaters is done through a onboard where there is a time tagged command, as I told you, where we can load certain command and giving one command what time you are supposed to execute. There are certain hardware features where a processor gets hung up. So automatically the processor changeover takes place, which is called FDIR. So these are some of the additional features, automated features available in the spacecraft. And finally, now every day, the satellite undergoes, we get a lot of data. Already I told you around 2000 plus parameters. So this subsystem is very trend analysis of each subsystem parameter, and each subsystem is a very crucial activity. We're looking at the previous day, whether the subsystem performance over a day is okay, subsystem performance over a week it is okay, subsystem performance with respect to last year it is okay. Because there may be, already I told you, there will be degradation in each kind of activities. So in order to find out the trend analysis is another major important. So subsystem engineers, they typically use different statistical and mathematical graphical tools and evaluate the performance. And finally, sometimes data may have to be ported. We have got tools to overlap the particular satellite data parameter over a day, over a month, over the years. Maybe sometimes you may have to overlap certain data across different spacecraft to look at the same parameter whether similar problem is. So we have softwares available, and all the softwares are developed in-house and developed by URSC team. And long-term trend analysis, already told you, these are the very important activity which are there. So typically, these are all some of the trend analysis one has to do, where battery condition performance, eclipse performance, solar radiation degradation, reaction wheel performance, thrusters performance, thermo-optical properties, and gyros drift trend and propellant pressure and other things. Some have listed certain things only. And similarly, another important activity is you have to exactly predict. This is very important because as I said, in the next slides, you will come to know why we will spend the remaining propellant of the satellite. So predicting exact life of the satellite is very important, because see, any large offset in the prediction will finally, we may not be able to track the satellite, because finally the antennas has to be correspondingly, as the satellite moves, if there is an inclination, if you are not able to maintain the inclination, finally antenna has to be tracked every day based on with respect to the profile. So, and finally the users now will have difficulty. So suppose if there is a propellant is going to end. We have to inform all the users in advance to shift to their services to other layer satellites. Okay, so predicting life of the satellite is very important activity. And finally, what happens is, I just to tell you, like, no, as long as there is no, so we have positioned the satellite, but once the satellite is positioned, there are certain enemies, like the lunisolar gravitational attraction pulls the satellite in the north-south directions. So that instead of normally initially the inclination, that is the angle subtended with the satellite orbit on the geostationary plane, equatorial plane will be 0. Because of the unidirectional pull of lunisolar gravitational attraction, satellite gets drifted in north-south direction. So we are allowed to the inclined orbit by a maximum of 0.1 degrees. Similarly, in the east-west direction, the Earth is not exactly spherical, it is gyroidal. And because the gravitation potential on the surface of the Earth varies from place to place. So this variation of gravitation potential on the surface of the Earth is called as triaxiality. And this triaxiality actually introduced a unidirectional acceleration, which is called tesselar acceleration, which is unwanted. Finally, it will have the implication on the change in longitude and immediately the semi-major axis. So finally, we are supposed to maintain the satellite within a longitudinal rectangular control box of plus or minus 0.1 degrees. Means that the satellite has, suppose if it is positioned at 74 degrees, satellite can have a maximum drift of in the north-south direction, 74 plus or minus 0.1 degrees. In the east-west direction also, it can drift by a maximum of plus or minus 0.1 degrees. I already told you, because of lunisolar perturbations, the satellite get drifted by in the north-south direction. So we allow the satellite orbit to be drifted by 0.1 degrees. So we have to bring the drifted satellite back to its position by changing the orbit plane. So we do almost 6 times a year. What is called, it is typically the solar gravitation force on the satellite orbit. So similarly, we orbit maintain, so we have to bring back the drifted satellite back to its position. So we do what we call it as north-south station maneuvers. We use small engines, what called thrusters. We fire for a duration, and we change the orbit plane from ascending node to descending node. So typically, so around per annum, we will have a total inclination change of 0.95 degrees per year, both lunisolar gravitational attraction. In the eastern direction, because of the Earth's triaxiality and the solar radiation pressure, there is a change in eccentricity in the A. So what I said is, so remaining 20% of the propellant which is carried out in the satellite is used for correcting the orbit correction, the inclination correction and the east-west correction we use. Okay. So there are certain constraints which are there. So when we plan the maneuvers, we must ensure that the eclipse is not there. And similarly, and when we have got a collocation of satellites, the first satellite in the chain the maneuver has to be done first, unless the lowest most satellite which is positioned in the collocated thing and done, the next satellite maneuver can. So when you have got sort of collocated satellite, maneuver planning will become a very crucial activity. So typically, other than that, other than 3 months in a year, almost 8 months in a year, we have to do these orbit rising maneuvers. This is a very complex activity. So this is what I am telling. We are also, and in the coming slides, I will just come to know satellite actually undergoes an eclipse almost 90 days in a year. So we cannot plan any north-south station keeping maneuver when the eclipse is going on, because the batteries undergoes a discharge during eclipse, and we have to recharge the batteries almost. So whole day batteries will be charging. So there are certain constraints where we cannot do the maneuver during the eclipse period. So this is what I was trying to sell. This is what I already told you. What is the sub-satellite point, where the imaginary line drawn from the satellite to the equatorial plane, where it cuts, that point is called the sub-satellite point. So we have to maintain the sub-satellite point within a control box of plus or minus 0.1 degrees. That's what east also you can go plus with respect to, for example, if I say here 74, suppose 74 is the satellite longitude, and north south also you can go by plus or minus 0.1 degrees, east west also. So we are supposed to control the satellite within this control box. So typically the quoted satellite, then it's another constraint. When you have more than one satellite position the same satellite in the longitude, we have to maintain a minimum inter-satellite distance of 10 kilometers. And because when you do the orbit determination to point out its position, the orbitation accuracy itself is 5 kilometers. So we have to maintain minimum more than 5 kilometers. So we maintain a minimum inter-satellite distance so that the satellite doesn't come and collide with each other. Similarly, that's what I was telling the east-west station keeping maneuver. And similarly, always because of the solar radiation pressure, we give certain and eccentric correction because we have to maintain the eccentric circle of each satellite within a certain value. So we do certain east-west maneuver, the eccentric correction maneuver by giving small pulses. And similarly, what happens is now, for example, we would have applied to an international telecommunication for a new longitudinal slot. The ITU will allocate a slot to you. Once one longitude is allocated, we have to place the satellite. We have to launch and position the satellite within a specified time period. Suppose if you don't place the satellite within the specified time period, the ITU has got the right to allocate that particular longitude to some other country. For some reason, you would have dedicated particular longitude to a particular satellite. For some reason, we are not able to achieve that mission in that year. In order to protect the life of the satellite, in order to protect the rights on the longitudinal slot, or when a satellite is, the new satellite is launched, before placing the satellite in the right position, we may have to assess the performance of the payloads, which is what IoT told you. So in that case, no, we may have to reposition. We may have to stop the satellite and do the IoT, then place the satellite, move the satellite. So the reposition requirement comes because of two reasons. One is for the IoT purpose. The second one is for to keep the rights, or it is like a double sat. Okay, so we have to claim the right. So in that case, so we have to so in that case, what we do, suppose if there is no launch, then in that case there are certain satellites who are getting aged, means that their fuel is going to end. As such, maintaining the satellite may not be of much use, and your users may not be able to track. So what we do, in order to protect the rights for the longitude, we move one of the old satellite to this new only, so that the right of the longitude. So we have to reposition the satellite. So what we do, we introduce a small drift, and the satellite starts getting drifted. And when the satellite comes to the intended position, we stop what already I told you. So this is repositioning is coming into picture. And reorbiting. So reorbiting is actually once the active lifespan of the satellite gets completed, we cannot position the satellite there. There are probably maybe 2 decades back, nobody was bothered because till each gram of fuel which is there, it is actually it earns a revenue. So nobody was interested to deorbit the satellite unless they lose it. So, but now because there is a international airbus management guidelines are there, once the satellite life is going to end, we have to reposition the satellite or reorbit the satellite. We have to push the satellite nearly 300 kilometers above the geostationary height, which is called the graveyard orbit or the super synchronous orbit. So it is a measure to reduce, so that we normally, once the end of life satellite is going to come, we have to re-orbit the satellite from the geostationary orbit to 300 kilometers above the geostationary orbit, which is called as graveyard orbit. So, okay. So now to transfer an existing aging satellite to a graveyard orbit, we need at least minimum 6 months of fuel, which is used for our NSSK operations. So this is the formula which is there, which is called, this is a formula which is used to find out what is that. Typically it comes to around 300 kilometers. So now, once we reorbit the satellite, before we switch off all the transponder and other things, all the energy or moving elements has to be disconnected because the satellite should not get exploded. So removing all the energy sources is called a passivation. What we do, we switch off all the rotating element, momentum element, we disable the battery charging, we completely disconnect the batteries, and if there is any fuel left out, we empty it and drain any energy dividing sources, and finally switch off the telemeter transmitter. Finally we say bye-bye. So this is what we call it passivation. So before switching off the transmitter, we have to ensure that all the rotating element, all the energy sources on the spacecraft are removed so that satellite doesn't disintegrate. Once the satellite is positioned in a graveyard orbit, it's like a dead body, it will be revolving, but it will not come back. So finally, because the geostationary orbit is too huge, it's not that crowded, but still it will all over a period of time, these junks will continue to increase the space debris. So debris monitoring is another important activity. The space debris may be the normal space junk or the space waste which is collecting around the Earth. These objects, instead starting from spent rockets or any of these potential, so debris monitoring and calculating is very, very important activity. Currently, MCF doesn't have the capability as such. So as and when required, we were using the facility of Indian Institute of Astrophysics and the Hanley telescope. So based on that, the MCF has planned to establish 2 optical telescopes, at one in Mount Abu at Panumudi, which is in order to track the Indian space asset, so that the 2 spacecraft geostationary orbit, they don't come and collide, so that if they come near, we do a conjunction analysis and take action so that they don't come. So debris monitoring is another important activity. So typically 90 days in a year, around the satellite experience explains the sun rays are blocked by this. Earth comes in the field of view of the sun, so there will not be any. So similarly, eclipse during shadow occurs twice in a year, typically during around equinox. So during that period, the critical subsystems on the satellite supported by batteries, and finally, and when the batteries are get discharged, and we discharge the battery, we recharge the batteries, we recharge the batteries at what rate, and finally these things are by control people, that by the satellite controllers. So typically you have a maximum eclipse duration of 72 minutes. It is something like a Gaussian distribution or a bell-shaped curve. It starts with a penumbra. You have an maximum of 72 degrees, start decreasing. Typically from August 29 to October 14, and similarly February 29th to April 14. So typically for 90 days and in a year, you have a satellite eclipse. So during the satellite eclipse, we don't do any maneuvers. That's what I said. Out of 12 months, 3 months in a year, we don't do a planned maneuvers. Remaining 9 months, we have to do the satellite orbit correction maneuvers. So MCF is busy. Everybody has to be kept at toes and do the repositioning maneuvers. Okay, eclipse already I told you. This is a satellite geometry where when you have the sun minus sun's longitude of 8.7 degrees, you get this. This is the sun's declination over a period of, it have an apparent motion of the sun minus 23.5 degrees. And similarly, you have a IRNS constellation, which is Indian GPS. We have got a seven satellite constellation. Some of them are in the geostationary orbit, some of them are the GSO with an inclined orbit. The first satellite is there as IRNS 1A. Now it is called a NVS. So typically, these are some of the frequencies which are used. And we have got the satellite, actually the bus commands are sent from Hassan, whereas the navigation and the grid correction commands are generated from the navigation control center at ISRO Bangalore, either at INC Bhopal or INC Lucknow or INC Bailalu. And these commands are generated every 5 minutes, and that is received at Hassan. The satellite, this is the typical 7 satellites which are there, and each of them is positioning how it is being positioned, and which of them are inclined, which is being the IRNS constellation. At any instant of time, 4 satellites are visible, so that we get both positional and the timing accuracy. And similarly, this is the coverage area, where which areas are being covered, what kind of air. So heart of the navigation satellite, you got a atomic clock, which is a rubidium atomic clock. So once, as long as the clock is working, you have the mission. So once the clock fails, the mission comes to an end. So this is the important activity. And typically, already I told you, the bus commands are sent from Hassan. And similarly, the navigation commands, which is for the grid correction or the positioning, are generated from the navigation control center at Bangalore and Lucknow. There are IRIM stations which do the ranging activity and sends the data. So in order to calibrate the activity, you have got laser ranging stations are available, and CDMA ranging stations are there. This is ground infrastructure space IRNS ground segment structure. And typically, we have what is called interference monitoring. So typically, once the satellite is positioned and the people start using, there may be some people who, like enemy countries, they try to interfere with our activities. So there are other satellite operating. So they may try to uplink and try to disturb. And some user may overshoot with this power bandwidth. Similarly, so we have to monitor the operations of the transponders or the channels. So finally, we have what is called interference monitoring, and if there are any violations by the different users and predict if somebody is overdriving, because we are supposed to operate the transponder with a specific coupling power. So we have to predict whether there somebody else is overstepping or some authorized users are there, they are trying to uplink. So all this detection and correction and the mitigation measures is done by what is called interface monitoring and this. So with this, I have made an attempt to complete the presentation. Okay, a little bit fast, but a lot of information is there. Hello? Hello?
Yes, sir. Yes, sir.
You are able to hear?
Yes, sir.
Yeah. So I have finished my presentation. Okay. So is there any specific questions? Okay, a lot of information was there. That's why I was forced to rush through, because already it has crossed 1 hour minute. Okay. Hello. Yes.
Yes, sir.
Yeah.
Sir, as you said, you give access to the many different stations to maintain the communication.
No, we are not giving.
Ongoing.
Let me be clear.
Okay.
We are not giving access to maintain our computer. We are accessing. We have our equipment positioned in intersite stations.
Okay.
Access our equipment. We also access. We have the access of their settings.
Okay.
They
Sir,
don't.
in that case, how do we maintain the security for confidential data, sir?
So confident, they are not able to access because his monitoring is control done from Hassan. They cannot access. Only equipment is sitting there. Okay, our equipment is sitting there. They don't have the access.
Okay, sir.
They are giving the place, but they are giving all the connectivity, the baseband connectivity, and the RF system they are providing. So our equipment is interfaced with their ground system, but we are able to access our equipment, which is the command encoder or the cortex, which is sitting there, or we will be able to access their cortex to see whether the required settings are they have made or not. To verify. We will not be able to what we call the control that, but at least we'll come to know what settings they have done.
Okay.
Yeah.
Sir, I have another one question. To fly anything, we require thrust. For thrust, we required hair, right?
What is it?
With sir, we required thrust for satellite, right?
Thrust for satellite.
Satellite to
No,
move in space.
no,
Satellite required thrust, right?
no. See, for example, when you position the satellite in a geostationary orbit, because of
Okay.
your uniform circular Earth's gravity itself will take care.
Okay.
You need not have to spend energy. Only thing is you have to position the satellite at a distance of 36,000 kilometers above the Earth's surface. Once you position the satellite at a distance of 36,000 kilometers, it is normal circular motion. Earth's gravity will take care. You have got centripetal centrifugal force balancing. Okay.
Okay, sir. Thank you, sir.
Because too much information was there. That's why I was a little bit fast. Sorry,
No
I
worries, sir. No worries.
apologize for that. But this is what exactly what we do in Hassan. That's why I have made it the topic is physics at play, because a lot of physical concepts are involved here.
I request if anyone are having any doubts, they can unmute yourself and ask the questions. So I think everyone are clear with the session.
Yeah.
Thank you for your valuable time. Thank you so much, sir.
Okay. Can I stop sharing?
Yes, sir.